All right, guys, let's get into the second video of the week. And like I said in the last video, I'm going to start doing it from your perspective. So I'm doing it through my student account instead of my teacher's account. So let's get started. All right, so taking a look at this, we're going to be studying using congruence similarity with triangles. So we have gone over some of the similarity rules, but now we're going to use it a little bit more to prove things. So let's see. In this lesson, we will apply congruence and similarity criteria to triangles to solve problems and prove relationships and geometric figures. So not necessarily just triangles, things in general. So by using these triangles, it's going to help us prove certain things like horizon sight, so how far we look up if we're looking at an angle of elevation versus an angle of depression. So just keep that in mind when we're looking up at something, it's elevation. If we're looking down at something, that's depression. All right. So let's kind of go through this and we're going to see how we can use certain criteria to help us out. All right, so using congruent. So being able to figure out when things are congruent, it can help us find small little angles like this, and it'll help us figure out these little smaller angles. So let's go into an actual problem. So let's take a look here. So a foreman at a landfill site is making an indirect measurement of the top of the garbage heap. In the activity, you will see how the foreman uses angles formed with the line of sight to determine how far the debris in the landfill is. So that idea of the pit that we saw, I'll just go back here. The idea of the pit and all of this is basically the ground level, and we can see that the garbage is down here. So let's take a look. Edmentum will make this look a lot, or Edmentum GeoGebra will make this look a lot nicer for us. And I have different drawing tools. I'll actually be able to write here. So let's take a look at this problem. So this is where we're looking. We're looking straight ahead. So that's why this is a 90-degree angle. And it's telling us to create a point AC. And then we want to measure that BAC. So angle A. So we create a point from A to C. So C is there. So let's create that line segment. And we're looking for this angle BAC, except we want to go counterclockwise. So remember going the opposite side of a clock. So we're going to go from C to B. So when we use our measuring tools, we're going to go here and we are going to do this. So we're going to go click, click, click. So our angle is 35 degrees. Presents that. What is angle BAC? So the measurement of angle BAC is equal to, and we don't say congruent, we just say equal to, because if we would say congruent, that would be if we're not putting the measurement. We're measuring this angle. This is the measurement of the angle, and it is 35 degrees. Put that there. Okay. And that looks like it's all it was asking us. Yeah. All right. So now create angle adjacent. So create an angle adjacent to ABC. So from A to B. So we're going to go, well, that is the angle. But measure the new angle from A. Okay. Create an angle adjacent to that using point A as a vertex and B as one of the sides. Okay. Measure the new angle equal to that. Extend the angle. Okay, so in other words, they want us to use the given angle. So what we're going to do here is we're going to use this measuring tool with a given angle. And we want it to be the other way. So this angle is counterclockwise because here's our line, and actually it's clockwise. Sorry, here's our line, and let's pretend this is 6 o'clock or 6 o'clock. Let's pretend this is 3 o'clock. Oh man, I'm tired. And we're going down to like 5 or 3 o'clock. So we're going clockwise. So we want to go upwards. So what we're going to do here is we're going to do this as our side. And we want our angle to be 35 degrees, not 45, 35 degrees. But we want it clockwise. So we're going to do that there. Counterclockwise. I said it like so many times and I didn't do it. So B to A, we want it counterclockwise. We want it the opposite way. There we go. And they want us to extend the array. So we're going to go to our construction tools. We're going to do array. This is our vertex. And we're going to draw the ray all the way over here. And we see that's 10 feet. So 35 degrees gives us like 10 feet up here. So when we do that, paste a screenshot, extend the ray, label the point of intersection with the ray, point D. So it wants us to grab a point. And we're going to do the intersection right there. And it wants us to take a screenshot. So as always, guys, just click the share, save it, give it a second for it to save, click that copy button, paste, and then what we're going to do here, just so we can have the picture too, that way when anyone looks at this, they don't have to click on it, even though they might want to. Let me see. This is the first time I've been as a student, so let me see if I can just paste it. I can't. I don't know what they did. So we are going to have to use the download button. I feel what they did was they didn't want people copying and pasting images. So now they have us like exporting the images. So we're going to go here to insert. We're going to find that picture that we just did. I believe it's in mine. It's in downloads. So did I just, that's not, that can't be it. Let me control where I saved it. I didn't control where I saved it. So let me download as, oh, not download. Let me export image. Download. I have it on the Kahoot quizzes, which if you guys are watching this kind of spoils something, but we'll see who gets this spoiled for. So let me go here. I'm going to go to download. Go here. Pop that there. Cool. And then there's my picture. And I'm not sure if you guys knew this, but you think you can, what you can do here is you can actually make this bigger, smaller by highlighting it and then doing this. So if you guys want a bigger picture, you guys can make it bigger. I'm not sure if you can crop it, but for the most part, you can at least make it bigger. How does triangle relate to that? So we're actually going to say that these are similar. And the reason why they're similar is we have an angle and the side. And also this is 90 degrees. So we're going to say that they are similar by angle, side, angle. Because this is also 90 degrees. It doesn't say it, but it's a straight line. This is 90 degrees, which means this is 90 degrees. So we're going to say that these triangles are congruent because of the angle side angle theorem of congruency. So because they're equal, we're going to end up knowing that this side that's 10 feet is going to be over here. So I forget, since I'm a student, I'm going to have to click on these pictures. All right, so let's take a look here. Where does it cross the marked line? What significance does this have for the land field problem. So it crosses the line at 10 feet. This means that the landfill starts at 10 feet. So I'm going to copy and paste this because I want to make sure I submitted these, so these are fine. But let me go back here. Oh, the garbage starts there. So this is the ground level, and the garbage is going to start at that 10 feet below. 10 feet below our line of sight. So go back here. Oh, and it saved it. Okay, 10 feet below our line of sight. I didn't say, I said landfill, but I meant to say the garbage. Garbage. You guys can always go back in case you guys don't know. So this one, I'm going to say, this is pretty easy. 5. This is similar to other things we have done in the let's get going. All right, so then this is at 10 feet, which means it's gonna end up being so if this is 4 feet, it's gonna end up being like 10 feet below ground. Oh, but there's a 0 here. I wonder where this 0 starts. Oh, 4 feet. Okay, so 4 feet plus 10 feet. So yeah, we're gonna do the same thing, except so 4 feet, and so this is 14 feet. So from here to here, it's 14 feet. So that 4 there, I don't know why they do it this way. This is kind of weird. All right, so let's take a look. We're looking at this distance in yards. So if this is 50 feet, and this is 75 feet. And we're going to assume that these angles are congruent. We're going to do, this has to be 75 yards because we're assuming that this angle is congruent, and because of angle, side, angle similarity, that means this has to be the same length. So this is like a tool that they use when they're like looking across like, oh, well, I know that from the tree to here is 50 feet, and I'm gonna mark something. So he's gonna look over a certain degree and kind of mark something there. So, well, first, let me kind of do this way. He is going to observe how far he sees here. And then what he's gonna do is observe something in the same angle but the opposite direction. So he's staring at this tree and he measures how far he's looking to see the rock over here. So then he's going to mark this, figure out this degree, and kind of start slowly making sure that it's the same degree. And then he can measure this. So he can measure how far the river is without actually having to cross the river. All right, so let's take a look here. Oh, so let me delete this. I believe it's this. Yep, got it. All right, so let's test this stuff out. So using GeoGebra, we're going to explore the triangles congruency. So we're going to prove some congruent triangles. We've already kind of done, I swear we've done this like a bunch of times. So they want us to prove it with side, 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 it looks like. So me being the lazy person I am, I'm literally just going to click this, click that, click that. So I have 5, 15, and 12. 0.65. So I'm assuming this is going to be 5. This is going to be that 12.65, and this is going to be that 15. So these are congruent by side, side, side. So AB is 5. BC is 12.56. and then 15. I don't know how I forgot the 15. I'm assuming these are corresponding. So I'm going to say these are 5, 12.56, and 15. I feel like the way Edmentum tries to get you guys to understand this isn't I think you can just recognize a pattern. You guys are smart enough to recognize patterns. So you're not really going to put much thought into this. They're trying to force you to think a certain way, which you can't control how other people think. You guys are all individuals. How are the triangles? So these are congruent because of the side congruency theorem. I feel like Edmentum wants you to learn certain things after they've already used them. It's like we've used side um, congruency before, so why are they teaching us about it now? Determine the length of the base of the corresponding height. So we want to do the corresponding height of this. So let's say we're going to do this. And we learned last time that the corresponding height would make 3 similar triangles. So what I'm going to do here to make this a little easier, well, actually this one I don't even have to do that much because it looks like it's already done perfectly for me. At least I'm assuming it is. Let's find out. So if this is a height, it should be 90 degrees. So give me a second here while I use my angle measuring tool. I am going to go counterclockwise. So C, D, B, yep, 90 degrees. So we see here that this measurement is going to be 4. So let's do this point perpendicular line. So I'm going to make a line perpendicular, and I'm going to go through this point, and I'm going to assume that this is also going to be 4. So I'm going to put a little dot right here, and I'm going to figure out how far that is by using my measuring tool for distance and length. Oh no. Do I don't know what it was doing. Yep, it's also 4 because I did 5 take away 4. All right, so determine the length of the corresponding height of ABC. The height is 4 because 5 take away 1 is 4. Brilliant thinking there. Oh wow, they're doing it all complicated. It's like, guys, you put it there. I can see it. I can see it right there. Determine the length of the height of this. How is this related? The height is also 4. They are the heights are congruent. Isn't that something, guys? Because these two triangles are congruent, they're going to have the same height. Wow. I feel like they're really trying to force ideas. And look at what they're doing here. They're figuring out the areas. When did they tell us to figure out the areas? Oh, they did tell us to figure out the areas. Find the areas. Ooh. So area of a triangle. The way I always remember area, guys, this is embarrassing, is this idea of if you have a rectangle's length times width. So if you cut that rectangle in half, you end up having this half of your length times your width. But for a triangle, we usually call it our height and our width. So let's kind of do this. So I'm going to clear all this. And our height was 4 and our length is 5. So we're going to do area equals, I don't want to go into the equation here, so I'm going to do 0.5 times 4 times 15. And then I'm going to say this is equal to half of 4 is 2 times 15. So then my answer ends up being 30. And guess what? I'm just going to copy and paste this over here. So the two congruent triangles have congruent areas. When the triangles are congruent, the heights are congruent. Guess what? That means that their areas are congruent. Awesome. Perform the sequence of rigid transformations in its position of the polygon ABC as vertices before performing the transformation. Also consider the grid, record the sequence of transformations, and calculate the area. Blah, blah, blah. I'm going to actually calculate the area in a different way. So they want rigid transformations. We're not going to use any dilation. So what I'm going to do here is I'm going to make this a polygon just to make this easier to move. If it's a polygon, I can move the whole thing. As lines and dots, I can't really do that. So what I'm just going to do here is I am just going to use my transformation tools. Where are my transformation tools? Oh, right here. And what I'm going to do here is I'm going to translate by vectors. I'm going to click this and move it. And then I want to rotate it. So I'm going to rotate it about a point. I'm going to use this point D because why not? Sure, 45 degrees, why not? Cool. So we see this triangle here. Instead of calculating the area all complicated, what you can actually do, it's one of the tools. Oh my gosh, where's the arrow? There we go. It's one of the tools in our measuring tools. You can just click area. And since this is a polygon, guess what? You click it, boom, your area is 30. So what did you do? I translated the shape and then rotated it and used the area measuring tool to confirm the area is congruent. That's all I'm doing here. I'm just saying like, hey, guess what? If you don't change the sides of it, it has the same area. So I feel that the ideas here are pretty obvious. Of course, a congruent shape has the same area. So it seems very obvious, but it is really important in the terms of math sense. It means that if you have a shape and you know they're congruent, you know that all the properties are the same. You know not only the sides are the same, the angles are the same, you know that their areas are the same as well. So that's all we're doing here, that congruent triangles have the same areas, same height. Okay, as part of the history project, we have a pyramid. So we have a pyramid. Let me see if I know how to draw a pyramid. I feel like I always forget how to do this. All right, let's say that's our pyramid. And then our height. So our height is 12 feet. All right, congruent triangles. Face, well, congruent. The student will be working on each face. Measurement. So the area is this. So what material will the student need to have the left face? So think of it this way. If we're looking at the height, pretend that I drew that straight. We have 12 feet here, and we have this slant height here. Okay, four faces of a triangle are congruent. Each face will have a different student texture. The student on the face needs to cover that. Okay, so if this is 12, I need to cover that much material. So I'm assuming what they mean is they're not talking about the height of the actual pyramid. I'm assuming they're talking about the height of the face, which would be 12, because we need another side of information if we want to find the height. So I'm going to assume that they're talking about the face is 12. So we're going to do half of 12 times whatever our base is. And wait. The student, he needs enough room to cover that much. How much material will the student need have left after doing the face? Wait. I feel like we're missing information here. 12 feet tall. The four faces of the pyramid will be congruent triangles. Each face will be given a different student in the group. The students are working on the back face of the pyramid, takes some measures, and determines that he will need enough to cover that much. So he's covering the back. Oh, I see. Duh. The triangles are all congruent, so it's just going to be 84. This 12 is just to throw you off. All of the sides are the same, so we're going to need the same amount. So now we're going to talk about similarities to help solve problems. So this idea of doing this, and this is going to have to do with proportionality. So think of it this way. If this side is over 30, then 20 is going to be over x. Well, we're going to say that these two are equal to each other. So if those two are equal to each other, then we can cross multiply. We get 60 equals 3x, and we find that it is x equals 20. Or we can just see it's like, hey, you just take this number, multiply it by 10, and you get this. So if you take this number, multiply it by 10, you get this. So you can do it by cross multiplication. It's supposed to be a 10. And you find that x equals 20. So because of the fact that these are similar, they're proportional. The sides are proportional. All right, so we're going to take a look at this. So the fire hydrant casts a shadow. So the shadow is 1.5. So this fire hydrant from here to here is 1.5. And it's going to cast a shadow. And the shadow, let me put it in yellow so we can see it better, is going to be 2.5. What is the height of the lamp post? Okay, so lamp post is going to have the same thing. So we're going to have 1 point, oof, geez. We're going to have 1.5 over 2.5, right? The shadow. And then this is going to equal, so our lamp post is this tall. So how tall is the shadow? Wait. Oh, the shadow is that tall. I'm sorry, we have these backwards. I thought this was going to be easy. It was just going to be like that. But the shadow is that tall. So we're unable to reach the height of the lamppost, but we know here, and we're trying to figure out x. So this, we can look at it, and it looks kind of complicated. It looks like if we divide this out, we can pretend that this is 15 over 25, which ends up being 3 over 5 is equal to x over 15. So if we think about it this way, by reducing it, we can go from here to here and multiply it by 3, which means we can go from here to here and multiply by 3. So I'm going to say 3 times 3 is 9. I'm going to say it's 9. Oops. What? No, I put the decimal there by accident. There we go. Really? 9 point nothing is wrong. And let's say you had doubts about this. Just remember, if we're going to do height over shadow, we need to do shadow over, or we need to do height over shadow. So this is the height over the shadow, height over the shadow. We just don't know what the height of the lamppost is. We can also do it by cross multiplying. So you could have done it like this, 2.5x equals times this, and I've mentioned it here before, but I always remember 15 times 15 is 225. In this case, though, since there's one number behind the decimal, there's also going to be one number behind the decimal here. I can grab a calculator and figure this out by doing 22.5 divided by 2.5. We get 9. I'm really annoyed at the fact that even though like 9 point should be the same as 9, it said I was wrong the first time. Alright, so let's see landscaping. So this guy's gonna landscaping. He starts off with a small triangle, and the rest have to be similar. Otherwise, the path, these little spots, won't have the same distance. They'll be weird. You want to make sure they have the same height. So let's take a look here. Similarity criteria. So we're gonna look at this, and they just want us to measure the height or the sides. So again, go to your measure tools, distance or length, click the side, click the side, click the side. Oh, I might want to move stuff around. So use your move arrow to kind of move these a little bit out of the way. Although I think I messed this up because this should go here, this should go over here. The reason why I know that is this is a hypotenuse. This should be bigger than that, and 0.8 is obviously bigger than 0.2. So let's kind of get into this. So AB is 7.8. 7.8. Our BC is our height, which is 3. And our base is 7.2. And what I can do here is I can type 0.5 times 7.2 times 3. Instead of doing half of the height, I don't like that the height is an odd number. So what I'm going to end up doing, I'm going to take half of the width, because I can take half of 72. Half of 7 is 3. We carry the 1 over here. Half of 12 is 6. And I'm going to put that decimal in the middle. Times 3. So 3 times 6 is 18. We have to carry that 1, though. So 3, 18, we have to carry, just so you guys can see it, we have to carry this 1 over here. So 3 times 3 is 9, plus that 1 is 10. So I should get 108 here. But one number's behind the decimal. So it's going to be 10.8. All right, I'm going to click this. And I get that. And guess what, guys? Another way of doing this would have been just to been like, I want the area of this shape. I don't know why they make us work with Edmentum, and then they're like, or I'm sorry, GeoGebra, and then they're like, only use some of these really good tools. All right, so now we want to make a dilation factor of 2. So I'm going to undo a lot of this because I don't want to see all of that stuff. So I'm going to do a dilation factor of 2 from the origin. So transformation tools, dilate, and click this shape here, and I want the factor to be 2. And what I'm going to do here is, again, I need the area, so I might as well just do this. They technically never told us to calculate the area. Oh, they want us to do ratios now. Got it. Okay, never mind. All right, so, and I know what they're going to do. They're going to do the ratios and then multiply them. So check this out. So we're going to do that. So if we look here, everything doubled. So this, the 7.8 doubled into 15.6. And if you guys want to see that visualized to make sure I'm not making it up. 15.6. BC doubled 2, so that's 6. And then if you take 7.2 times 2, you get 14.14. We're going to take the new divided by the old. So if everything doubled, then this should be 2, this should be 2, and this should be 2. All right, determine what the ratio of the area. What is the ratio of the area? Ratio is 2. What is the ratio of the area to the ratio is 2. The ratio of the area is 2 for, unfortunately, we do have to use the equation editor for this. We have 2 triangles. One of them is A prime, so you can just use an apostrophe here, A prime, B prime, C prime, to A, B, C. There we go. All right, and now we want to do the dilation factor. So what are we doing here? Ratio of area to that. Okay, apparently we're not calculating the area. Now we're doing something completely different. So reflect across the x-axis and dilate by half. Okay, so we're gonna take, is it the original one? Yeah, we're gonna take the original square. We're gonna reflect off the x-axis. So we're gonna do reflection about up the, reflect this over the x-axis, and then it wants us to dilate it by a factor of 0.5. So I'm going to grab this, dilate it, and the factor is a half, or 0.5. And look how tiny it is, how small, half as small to be exact. Get rid of these. All right, cool. So rotate it 90 degrees and dilate. What? Oh, these are 2 different things. Oh, so this is the first task. All right, so the dilation factor, 0.5 of the area. Well, it's half. Oh, it wants us to type the actual area. So go here, get the area, boom, get 2.7. So we do 2.7. Ratio of the area of the triangle, it's going to be 0.5. I don't understand why it's doing this to us, guys. I'm so sorry. So if we take half of this, so if we take half of 10.8, 10.8 divided by 2, we get 5.4, which is, what happened? Which one did I take half of? Over, did I take the right area? What happened here? This area is 10. Oh, that's right. We're not cutting it in half. Ah, they got me. The reason why we're not cutting this in half is area is not a one-dimensional thing. They'll explain this later. Um, Area is not one dimension. It's 2 dimensions. So if we have this 0.5, we have to square it. So the dimension of the area would be 0.5. So what's going to happen here is we're going to do this 2.7 divided by 10.8. And if we divided that out, we would get this 0.25. Remember, it's always new divided by old. All right, and the next one, it wants us to rotate it 90 degrees and increase it by a factor of that. So, all right, clockwise or counterclockwise? Counterclockwise. All right, cool. So I'm going to do my transformation tools, rotate. No, not that one. 90 degrees. And it wants us to rotate counterclockwise. So we have that. And then it wants us to do dilation of 2.5. So go to dilation here to here, 2.5. So the way I explained it, again, we're not dealing with one dimension anymore. We're dealing with two dimensions. So 25 times 25. I used to know. I want to say 625. I memorized this at some point in time. All right, 625. But since we have two numbers behind the decimal, it's going to be 6.25 is big. You'll see this, so give me a second here. So the dilation factor is 5. Here, we're going to say that this is, I have to take the area. So grab this, measure the area, 67.5. 67.5. So let's see how right I was, guys. So 67.5 divided by 10.8. It's always new divided by old. So clear this out. I was clicking like a million times because I'm never sure if it does it. And we get 6.25. 6.25, which is what I predicted. I keep forgetting to hit the submit button on these. All right. And so the ratio. Find the ratio of this. So we're basically HI. This one, I don't see why we're doing this. This one, I already know for a fact. Oh, the ratio from HI to that. Oh, okay. So let's think of it this way. If we already know this ratio and then this ratio, we can essentially say that one of them is half as big as the original and the other one was 2.5. So the ratio ends up being a lot. Give me a second here. You can imagine it as this and this. And what would happen here is we end up getting this 5 times as big. In theory, let's see how it is in practice. So we've seen how area doesn't always work out that way. So let's see what happens here. So we're going to take, I'm going to delete some of this information. So I don't need all of this right now. So all I'm going to do is the same side because we don't really need the information. It's just asking us for the ratio. So we're going to grab this. We're going to do the HI, our hypotenuse. And we're going to do this hypotenuse, which is super teeny tiny. Hopefully I got it. To 3.9. So I'm going to do it. It says HI on the top, right? So big over the top one. So 19.5. Clear this out. 19.5 divided by, what was that tiny number again? 3.9. 3.95. Exactly what predicted. And again, guys, work smarter, not harder. I don't know why I really phoned this in. Now we're going to take the areas. So again, we're going to take the bigger one first. The bigger one, we can just take the area from here. And remember, I said it's two dimensions, so this should be 25. Let's see how right I am. I get how Edmentum teaches, I really do, but I feel it kind of teaches things out of order. And that is 27. Is there a round off error somewhere? Give me a second. 67.5 divided by 2.7. Yeah, okay. I must have typed in the wrong number there somewhere. I'm sure you guys can probably rewind and see what I did, but I don't want to pause the recording and then try to figure out what's going on. All right. Based on the observations, what can you conclude about the ratio of the sides? Area is going to be squared of the ratio of the sides. And I kind of knew this going in because I've dealt with areas before, but I'm sure you guys are kind of like, how did he know that? Or how did he realize he was wrong the first time? Let's think of it this way. So if we look way back when we were over here, oops, I forgot to put the 10.8, whatever. When we looked over here, we were doubling the area of the length. The lengths were double, but then all we did was the area. So these were double, but the areas end up being a lot bigger. They were like 4 times bigger. We were essentially just squaring them. So it went from 2 to 4, and let's pretend I didn't know that. Let's pretend I didn't know that at all. When we dealt with this, which one of them was 5 times bigger, and we got something that's 25 times. Well, how do we get from 5 to 25? 5 times 5. And how do we get from 2 to 4 times? The ratio of the areas is, 4 times. Ratio of areas. The areas were 4 times bigger. I forgot to correct that. Make sure you guys correct it. So 2 times 2 is 4. So we're not just doubling it. And then we're like, oh, this one we're not, it would have been 10 if we just doubled it, but we're just squaring it. So I can hit this and it'll kind of explain the ratio, triangle, similar squares. So they're squaring the ratios. I thought the areas would have the same ratio. It turns out to be squared. So don't just write like any random thing. Write any challenges you have. In this one, I was so bored with how they were doing the other one. I just went and assumed that we were just doubling it, but we weren't. They were actually teaching us something. Good job, Edmentum. You were teaching us something. So we're just squaring the areas. So we take the ratios and square them, and that's how we figure out the areas. So if we take a look at this one, let's calculate the area for this, and we notice that this area, this triangle, is half of this triangle. All right, so that means that we're going to take half of the area, squared it, which means it should be 1/4. So because the ratio, so it's the sides squared, the proportion of the sides, proportion of the sides, and then we square them. Okay, so the proportion of sides 1/2, so it's 1/4. So what we're going to do here, we're going to take half of 8.4. We're going to multiply that by 3.36. So half of 8 is 4. Half of 4 is 2. So that's how we get half of 8.4. And we're going to multiply that by 3.36. So I'm just doing, I'm sorry, I didn't explain it. 1/2 the base. So I'm going to pretend this is the base times the height. Because if I would have laid it flat, that's how it would have looked like. So here I'm going to go back to my mouse mode. 4.2 times 3.36. And I was not typing. 4.2 times 3.36. About that. And we want to divide this by 4 because it's not half of it. Half squared is a fourth. So we're dividing by 4. So I'm going to get 3.528. And they show all of it right here. If they're doing the 3/8, they're calculating. They calculated the area. I don't know how they're doing this. This one's weird. Oh, so there's the area. Half of this. So they're doing half of the area. And then they're going to square it. So I don't know how they're getting this 3/4. That's just weird to me. They're doing weird stuff, guys. If you want, just rewind what I did. I know how they're doing this, but I think they're assuming a lot. Like, they're assuming that you know it's like 1/2. Oh, 1/2 squared. Where are they getting the 3/4? Oh, I see. They're taking this 3 and this 4th. Okay. They're doing a lot more work than I would have done. All right. Last activity. Now we're going to talk about perimeter. Well, guess what? Perimeter, unlike area, only has one dimension. We're essentially just measuring this line plus this line plus this line plus this line, which is the same thing, kind of just like this, 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 that. It's one dimension, one line. Area involves us doing 2 dimensions because area is basically all of these little squares inside making the area. All right, so what is the perimeter? I don't think there's a tool to measure perimeter. If there is, that'd be interesting. Let's see. Similarity. So let's take a look at these triangles. Measuring tools. We have area. We don't have the entire perimeter. So we're just going to have to add all of them together. So let's take all the sides. So if we use a calculator, I'm just going to use the Windows calculator. That way I don't have to go to another screen to do it. 5 plus 11. I find that it's this. So I'm going to do all of that here. So 7.8 plus 1.2 plus 5 equals, what was it, 24? 24. What I did here was, since I'm using the Windows, I just kind of took my taskbar, put it here, so it kind of makes a little useful thing. You guys can use your calculator here if you want. I find it funny how I have them lined up pretty similar. And then they're doing that. They're just adding all the sides together. Oh, we're doing 2 things again. All right, so first things first, we want to dilate it by a factor of 2. So we're going to take, I'm just going to make a random point. I won't make it random, I'll just make it here. And ratio of the perimeter, blah, blah, blah. So the perimeter, again, they're making us do more work for, instead of like explaining to us like, hey, you know, perimeter is one dimension. I'm just going to go through this. I'm going to say it is 48. Why? Because our scale factor is 2. And the next one, well, I'm going to take that 24. And you know what? I'm even going to show it right here, just so I know what I'm doing. So that's going to be the 2 times 24. And over here, I'm going to do 2.5 times 24. I'm going to say this is equal to, grab my calculator, multiply this by 2.5, 60. 60. What is the ratio of the perimeters? 2. 2.5. They're one dimensional. I can prove that, but again, if I shrink this, if all I'm doing is adding all this, think of it this way. All right, let's say I had 2 plus 4 plus 8, and then I cut all of these in half. 1 plus 2 plus 4. I end up getting 7, whereas if I added these together, they were 14. Obviously, just by adding sides, we're doing this. The reason why it's different with area is if we have 2 times 4, and we get 8. But if I cut these things in half, the sides of my triangles in half, I get 1 times 2. This is only 2. We're dealing with 2 completely different dimensions here. So that's why things change. All right. To go here. So what does the scale factor of these show? Perimeters have the same scale factor as their sides. So where before it was just the scale factor is the side squared, this one is they're equal. Scale factors are equal. All right, so then we're going to do this. So find the ratios of the corresponding side lengths. Oh, come on. They told us what the scale factor was. Oh, but we're doing it from one. Nope. Nope. I thought we were doing it from one to the other, and they're like, nope. They're just. Oh, yes, it is. Prime. Okay. So, just to kind of show this, so I am going to end up having to do the work anyways, guys. I'm sorry. Well, this will at least help you see what we were supposed to do anyway. So, let's take a look here. So, one of them, I am doubling it. So, I'm going to use my transformation tools. I'm going to dilate it. Where's the dilation? And again, rotation, all that stuff doesn't affect change. I think we've done that a few times. Rotation, rigid transformation doesn't affect size. And then we're going to do this again, but this time at 2.5. And you can see that we can actually see the side lengths. So I'm going to do this. Let me grab a pen. 28 over the 2.4. So if I do that, give me a second here. Calculator. 28 divided by 2.4. I get 1.25. 1.25. Obviously, the rest are going to be the same. I really hate how it does it. It should only ask you to compare one side, not all of them. We already know that all of them are going to have the same thing. We've done this several times already. And I feel like it loses your attention. You guys probably zoned me out a while ago. All right. So the next thing we're going to do here is we are basically going to compare the sides. So think of it this way. One of them was 2.5, the other one was 2. If I divide this out, let's see what happens. 2.5 divided by 2, 1.25. What a shocker. So now find the perimeter of these compared to each other. Oh, come on. Obviously, if they're proportional, then they're proportional. The sides will have the same proportionality as their perimeter as previously stated. Sorry, I got a little snarky on that one because it's very repetitive. Like, we just found out that if we take the ratio of the sides, the perimeters have that same ratio. So why are we going to do it again? We proved it over here. Where was it? Over here. So I don't know. I don't see why we have to measure more than one ratio if we know they will all be the same. I really hope you guys don't hear uh, they're cutting the grass outside, and I swear I feel like they do it every time I'm about to record. So let's try to get this done. I submitted everything. Oh no, Well, luckily I submitted everything. So it's this idea that the proportionality of the sides is going to be the same as the proportionality of the perimeter. Or I should phrase it this way. The proportionality of the perimeter is going to be the same proportionality of the sides. Basically, if you do 9 over 3, so we're doing 9 divided by 3, that means whatever this area is, if you multiply this area by 3, you get this. If you take this area and divide it by 3, you would get the area of this triangle. All right, so they want us to do a proof. Notice that they didn't do this with the area one. They're only doing this with the perimeter because it's a lot harder to do. So let's kind of think of this way. The find ratio of a triangle. So the find ratio R of the triangle. So given so the ratio of this triangle, let's assume we're doing AB. So it's C divided by F. Okay, so R is C divided by F or B divided by E. So these are the ratios, R. And then we're going to do cross product. So we're going to multiply this. So I'm assuming we're going to use the first two. So I'm thinking we're going to do AE equals BD. AE equals BD. Where are AD? What ratio are we doing here? Because we have multiple ones. I can do AD is equal to CF, and that's going to be completely different. So let's take a look here. Oh, I see. We're going to ignore these two. We're going to say this. So we're going to multiply both sides by D. Okay, I see what they're doing. I'm assuming I see what they're doing. So I'm assuming they're doing this. R over 1 equals AD. Or you can say R over 1 equals BE. And you cross product it, so you get B equals RB. RE, I'm sorry, RE. Obviously, it's not the same thing, RE. Or you can get this as A equals RD, which is right here. So I'm assuming that's what they mean by cross product. Yep, I was right. And then definition of perimeter. So definition of perimeter, they just want us to add all the A's together. So we're going to do this A plus B plus C. So perimeter 1 is, they're doing definition of perimeter and substitution. So they're doing A plus B plus, let me write it down. P1 equals A plus B plus C. But instead of doing that, they're going to do this RD. Unless I'm missing something. Oh, never mind. I thought they were going to skip a step. I was like, Edmentum, stop it. Now they're going to use definition of, so the second perimeter. So this is the second perimeter. And now they're going to do substitutions. So we're going to do the substituting property. So give me a second here. We're going to substitute A with RD. So it's going to be RD, and we're going to substitute B, this B right here, with this RE. So that's this formula right here. These all have these R's. And then they're going to do backwards distributive property. It says distributive property, but this is technically supposed to be the word factoring. You guys might have learned that in your Algebra 1 class. You'll definitely do it in your Algebra 2 class. And now we're going to factor this. So in other words, we're going to, or substitute. So what is this? Well, this is P2. So we're going to say R times P2. Therefore, the ratio between these perimeters is that. All right. And then remember to study your summary, guys, about proportionalities and ratios. The most important one, I think, is the one about areas. That one I think is harder because R of areas is going to be, let's say 2. I want new over old. New over old. Come on, Victor. It's going to be this. I'm saying the sides of it squared. So R of areas, the ratio of areas, is going to be the ratio of sides squared. So the ratio of the areas is equal to the ratio of the sides squared. Alright, guys. So I'll see you in class. Hopefully that helps you guys.